Alright, let's go. Number 10. The first observer problem. In 1978, John Wheeler was teaching a graduate seminar in general relativity at the University of Texas at Austin. A student kept pressing him on the double-slit experiment, the one where a single photon behaves as a wave, producing an interference pattern right up until you install a detector at one slit, at which point the pattern vanishes. Wheeler didn't have a clean answer. He sat down and tried to work out how far back in time that measurement could reach. Standard quantum mechanics is unambiguous about the rule. A system exists in a superposition of possible outcomes until an observation forces it into one. In a lab, this works cleanly. Detectors click. Meters read. The wave function collapses to a definite value. The mechanism requires only that some observer at some point interact with the system. That interaction always happens in practice. Wind the clock back. Past star formation. Past recombination. Past the first 1032 seconds after the Big Bang. Every particle in the observable universe is in superposition. There are no detectors. There are no observers. There is nothing to collapse anything into anything. Wheeler formalized the paradox in his 1978 essay on the delayed choice experiment, published in the volume Mathematical Foundations of Quantum Theory, edited by A.R. Marlowe. He extended it in a 1983 essay titled Law Without Law in the collection Quantum Theory and Measurement, arguing that observations made in a laboratory today retroactively fix the states of photons emitted by quasars 10 billion years ago. He gave the process a name: Genesis by observership. Every escape route has taken damage on inspection. H. Dieter Zay's decoherence framework, introduced in a 1970 paper in Foundations of Physics, argued that environmental interactions produce apparent collapse without any observer, but decoherence still needs a system and an environment to be distinct, and the homogeneous early universe does not provide that split. Hugh Everett's many worlds interpretation eliminates collapse by branching every possibility into its own universe, at the price of an infinite ensemble and no account of why we occupy this branch. Wojciech inselection work at Los Alamos refined the machinery through the 1990s. The pre-inflation problem remained. Christopher Fuchs's cubism reframed quantum probabilities as agents' personal beliefs, a philosophical retreat, not a physical answer. Every carbon nucleus in your body had to become a definite thing at some point. Its state was either fixed by an observation that already happened, or, on Wheeler's account, by an observation happening now in your reading of this sentence, reaching backward through 13.8 billion years to fix the past you inherited. If the universe had to wait for an observer to become itself, what was it, exactly? In the meantime, that entry hid an observation problem. This one hides a direction we can't explain. Number 9. The Axis of Evil. Kate Land and Ju Mugwejo, working at Imperial College London in 2005, were checking the largest scale features of the cosmic microwave background using WMAP's second-year data release. They looked at the quadrupole and octopole moments, the two lowest frequency ripples in the map of the sky at 2.7 Kelvin. The check was routine. The math was standard. What came out was neither. Inflationary cosmology predicts, with mathematical precision, that the cosmic microwave background should be statistically isotropic. The temperature fluctuations across the sky should have no preferred direction. That is the point of inflation, a rapid early expansion that smooths every local variation into a uniform background. The largest scale should be the most uniform. There should be no cosmic axis to find. Land and Mugwejo found one. The quadrupole and octopole components lined up with each other. And that combined axis lined up with the ecliptic plane of the solar system, the flat disk traced out by the planets orbiting the sun. Their result appeared in Physical Review Letters, Volume 95, Article 071301, in August 2005. The alignment between the quadrupole and octopole moments was significant at roughly the 99.9% level relative to isotropic simulations. The correlation with the ecliptic plane showed up at a similar level. They gave the anomaly the name it kept, the Axis of Evil. Contamination checks have not made it go away. Foreground removal was rerun with independent pipelines by the map team, and later by Planck, the alignment survived. Zodiacal dust along the ecliptic was modeled and subtracted. The correlation remained. Alexei Starobinsky and others argued the Lowell anomalies were nothing more than cosmic variance. But the joint probability of quadrupole-octupole alignment plus ecliptic correlation plus a hemispherical asymmetry sits below 1 in 10,000 in most independent analyses. Craig Copey, Dragan Huderer, and Dominic Schwartz confirmed the alignment survived into Planck's 2013 data. No mechanism in standard cosmology predicts why the largest structure in the visible sky should know anything about a planetary disk that formed 9.3 billion years after the CMB was emitted. The oldest light in the universe carries a direction, and that direction is your solar system's plane. Every night you look up, you are looking at radiation from 8 billion years ago that appears to be organized around the plane your Earth orbits in. How does a signal from 13.8 billion years ago encode a preferred direction that matches a solar system 9.3 billion years younger than the signal itself? The universe knew where we'd be. The next one asks why where exists. Number 8. The pre-geometric phase. Lee Smolin spent the late 1990s at the Center for Gravitational Physics and Geometry at Penn State, trying to quantize general relativity without smuggling spacetime in as a background assumption. He wanted a theory of gravity that did not already need gravity to formulate. Fotini Markopoulou, a young researcher pursuing the same problem, was developing network-based mathematics for the same purpose. Neither of them started with space and time as given. Every physics you learned in school assumes a stage. Particles move on it. Fields fill it. The stage, space, time, geometry gets treated as given. Even standard quantum field theory sits atop a fixed spacetime background. Einstein's general relativity made the stage dynamical, but it kept the stage. Everything happens somewhere. Everything happens at some time. Loop quantum gravity says the stage is not fundamental. Space is emergent, built from discrete quanta of area and volume linked in a network. Time is emergent, made of transitions between those network configurations. Below the Planck scale, there is no here. There is no now. Smolin laid out the argument for a general audience in 3 Roads to Quantum Gravity, published by Basic Books in 2001, and the technical case in The Life of the Cosmos in 1997. Markopoulou developed causal spin network formalisms through the late 1990s and early 2000s that made pre-geometric evolution mathematically explicit. Carlo Rovelli's textbook Quantum Gravity, published by Cambridge University Press in 2004, formalized the framework. No competing quantum gravity program has closed the gap. String theory replaces particle points with vibrating strings but still requires a background spacetime to define the strings on, a feature its critics have flagged for 4 decades. Asymptotic safety, proposed by Steven Weinberg in 1979 and pursued by Martin Reuter's group at Mainz, tries to salvage a background but has not produced a testable pre-Big Bang prediction. Causal dynamical triangulations, developed by Jan Amjern, Renat Lal, and Jerzy Jurkiewicz, generates emergent spacetime numerically, but only in simplified cases, and only for 4 dimensions in a tuned regime. No model has produced a checkable pre-geometric prediction. The location of your body, the fact that you are here, now, at these particular coordinates, may be an emergent property derived from something more fundamental that has no location and no time. Your address in the universe may not be primary. It may be an approximation. If space is made of something, does that something have a shape? And if it doesn't, what is it made of? Space itself may be derived. This next entry involves a number that isn't. Number 7. The cosmological constant's pre-existing value. Einstein added a term to his field equations in 1917, the cosmological constant denoted to keep the universe static under the influence of gravity. He removed it in 1931 after Edwin Hubble's redshift data showed the universe was expanding, and reportedly called it his biggest blunder. 71 years later, two teams of astronomers, Saul Perlmutter at Berkeley and the High-Z team led by Brian Schmidt and Adam Rees, were measuring the brightness of Type 1 supernovae to determine how fast cosmic expansion was slowing down. Expansion was assumed to be decelerating. Gravity, whether from ordinary matter or dark matter, pulls things together. Even optimistic models expected the expansion rate to be declining over cosmic time. The supernovae, treated as standard candles at a known intrinsic luminosity, were supposed to confirm the rate of that deceleration to a few decimal places. Both teams found the opposite in 1998. The universe was not slowing down. It was accelerating. Something was pushing space apart against gravity's pull. Einstein's discarded constant was back, and it was doing the work. Rees and colleagues published their result in the Astronomical Journal, Volume 116, in September 1998. Perlmutter's team followed in the Astrophysical Journal, Volume 517, in June 1999. The vacuum energy density measured from those observations is roughly 610 joules per cubic meter. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics. The number itself has never been explained. Quantum field theory predicts a vacuum energy from 0-point fluctuations of all the fields in nature. When you calculate it with a Planck scale cutoff, you get a value 10,120 times larger than what's observed. That is the worst quantitative prediction in the history of physics. The anthropic principle, promoted by Steven Weinberg in a 1987 Physical Review Letters paper, argues we observe this specific tiny value because larger values would have prevented galaxies from forming and thus prevented us. But this requires an ensemble of universes with different values, none of which anyone has ever detected. The string landscape, with roughly 10,500 possible vacua, has no mechanism for selecting one of them. Dynamical dark energy models, quintessence, phantom fields, swap the constant for a field with a value nobody can predict either. If the vacuum energy density had been slightly larger, matter could never have clumped. No galaxies, no stars, no planets, no carbon, no you. The number that determined whether the universe could build atoms was already set at the moment of the Big Bang, inherited from something we cannot see or test. Where did the value come from, if the universe inherited it rather than chose it? That number decided whether atoms could form. The next one may still be generating new ones. Number 6. Eternal inflation's parent vacuum. Alan Guth was a Cornell postdoc in 1979, working on grand unified theories and trying to explain why the universe appeared magnetically monopole-free, despite the fact that gut theories predicted heavy monopolies should have been abundantly produced in the early universe. His notebook entry from December 6, 1979, reads, "Spectacular realization." The same mechanism that suppressed monopolies could also solve the horizon and flatness problems. He called it inflation. In Guth's original model, inflation was a brief phase, 1036 to 1032 seconds after the Big Bang, during which space doubled in size roughly every 1037 seconds, driven by a false vacuum with a specific negative pressure equation of state. The inflaton field then decayed, released its energy as radiation, and normal Big Bang cosmology took over. Inflation was supposed to end. Andre Linde showed in 1986 that it does not. If inflation ever starts, quantum fluctuations in the inflaton field cause it to continue in some regions even as it ends in others. Inflation, once initiated, never fully stops anywhere. It only ends locally, in pockets. Our observable universe is one such pocket. Linde's chaotic inflation paper appeared in Physics Letters B, Volume 129 in 1983. The eternal inflation extension came in Physics Letters B, Volume 175 in 1986, under the title Eternally Existing Self-Reproducing Chaotic Inflationary Universe. Linde developed the model further through the 1990s. The current inflationary paradigm, the framework underlying nearly all modern cosmology, is a variant on his approach. The alternatives all leak the same way. The ekpyrotic model, proposed by Paul Steinhardt and Neil Turok in 2001, replaces inflation with a collision of branes in higher dimensional space, but the branes themselves are eternal, or come from a prior collision. or emerge from something else. The cyclic universe model inherits the same regression across cosmic epochs. Loop quantum bounce cosmology, developed by Abhay Ashtakar's group at Penn State, replaces the singularity with a bounce. But the pre-bounce state has to come from somewhere. In 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin published a theorem in Physical Review Letters proving that any average expanding universe must have a past boundary, ruling out simple, eternal past inflation. Nobody has produced a beginning that does not need a prior thing. Your Big Bang was a local event, somewhere outside your cosmological horizon. The parent inflationary field may still be producing new universes right now, with different physical constants at a rate you have no way to observe or measure. Does the regression bottom out anywhere, or does the chain of what came before just keep going up? The parent process may still be running. The next entry is the echo we sought. Number 5. The primordial gravitational wave background. John Kovac at the Harvard-Smithsonian Center for Astrophysics led the second-generation BICEP telescope through the early 2010s at the Amundsen-Scott South Pole Station. The instrument was a 26-centimeter refractor pointed at a specific patch of the southern sky, roughly 380 square degrees, in a region of low galactic foreground contamination. The team was looking for a very specific polarization pattern in the cosmic microwave background, B modes, that only primordial gravitational waves could produce. Inflation predicts that quantum fluctuations of space-time itself, stretched by exponential expansion, produce a background of gravitational waves. Those waves imprint a distinctive curl pattern on the polarization of the CMB, B modes, with an amplitude set by the tensor to scalar ratio R. A detection of R above zero would be a direct measurement of space-time dynamics from 1036 seconds after the Big Bang. On March 17, 2014, Kovac's team announced a detection of B modes consistent with R.20, well above zero, well above expectations. Press conferences were held. Physicists were filmed being told their life's work had been vindicated. The paper was submitted. The result was published as BICEP2 Collaboration et al. In Physical Review Letters, Volume 112, Article 241101 in June 2014. In September 2014, the Planck satellite team released polarization data, showing the region observed by BICEP2 had significantly more galactic dust than the original analysis had assumed. A joint BICEP2 Keck-Planck analysis in 2015 found the primordial signal was consistent with zero. The latest constraint from BICEP Keck 2021 combined with Planck is R0.036. The search has not stopped, but every strategy faces the same wall. Ground-based instruments like the Simons Observatory, under construction in the Atacama Desert, target R as low as 0.003. Light BIRD, a Japanese satellite scheduled to launch in the early 2030s, is designed for even deeper sensitivity. CMB-S4, an international ground-based effort planned for the South Pole and Chile, aims at R near 10.3. Each program depends on future funding, future launches, or future data. If R turns out smaller than 10.3, the primordial signal may sit permanently below the noise floor set by galactic dust and gravitational lensing. Humans may be looking for something we can never see. A confirmed detection would be the earliest direct information we have ever recovered about anything. A signal from an epoch, when the universe was 1036 seconds old. A permanent non-detection would leave the first moment behind a wall we cannot cross. If the signal from the Planck scale universe is unreachable, what does it mean to call that moment part of physics? That echo may never reach us. The next entry doubts a first moment existed. Number 4. Pre-Big Bang string gas. Robert Brandenberger at Brown University and Qumran Vafa at Harvard were working on the thermodynamics of fundamental strings in the late 1980s, the one-dimensional objects that string theory proposes as the basic constituents of matter and force. They noticed that the standard picture of the Big Bang, in which the universe expands from a singularity, does not quite work when your fundamental objects are strings rather than point particles. In a universe of point particles, cranking temperature up cranks kinetic energy up. Higher temperature, faster motion, higher energy density. This works up to the Planck temperature of roughly 1032 Kelvin, at which point classical general relativity breaks down and the singularity of the Big Bang is reached. Standard cosmology treats that singularity as the beginning of time. Strings behave differently. Above a critical temperature, the Hagedorn temperature, roughly 1030 Kelvin for typical string models. Adding more energy to a system of strings does not raise the temperature further. It creates more strings. The system saturates. Temperature plateaus. Brandenburger and Vafa published their proposal as superstrings in the Early Universe in Nuclear Physics B, Volume 316, in 1989. The Hagedorn temperature itself had been derived by Rolf Hagedorn at CERN in 1965 for hadronic matter, before anyone knew it had a fundamental string interpretation. The Brandenburger-Vafa model requires 9 or 10 spatial dimensions initially, and proposes that only 3 of them ever grow to macroscopic size, a feature they attempted to derive from the topology of string interactions. Attempts to match the model to data have consistently faltered. Explaining why exactly 3 dimensions grew, and not 2 or 4, requires a specific set of string winding assumptions that other calculations have not confirmed. Predictions for the tensor-to-scalar ratio and the spectrum of primordial fluctuations come out ambiguous, depending on which submodel you adopt. Ali Nayeri, Brandenburger, and Vafa's 2006 update in Physical Review Letters was later challenged on the grounds that its calculation of the perturbation spectrum was more sensitive to unknown Planck scale physics than the original paper had claimed. The model has not been ruled out. It has also not been confirmed. On the Brandenburger-Vafa model, the universe existed for an indefinitely long period in a hot, static, densely stringy state before the moment we call the Big Bang. That moment was a phase transition, strings unwound enough for space to start expanding. Nothing about it marks a genuine origin. If there was no beginning to explain, what were we explaining when we said Big Bang? One model borrows time from before time. The next one borrows an entire earlier universe. Number 3. The Conformal Cyclic Cosmology. Roger Penrose returned in the mid-2000s to a paradox he had been chewing on for decades, the Weyl curvature hypothesis, which asks why the early universe had such extraordinarily low gravitational entropy. Something had to have arranged roughly 1090 particles into a nearly uniform low-entropy state at the Big Bang. Standard cosmology has no mechanism for this initial condition. Penrose decided it had to have come from somewhere. 10 to the 100th power years from now, all matter will have decayed, all black holes will have evaporated by Hawking radiation, and only massless particles like photons will remain. In a universe with no massive particles, no scale exists. No rulers, no clocks. General relativity in this state is conformally invariant. You can rescale distances and times freely without changing the physics. Penrose noticed that a Big Bang, before any structure has formed, has the same property. A universe made only of massless quanta is mathematically equivalent to a universe at the start of everything. The end of time and the beginning of the next time become the same object. Penrose published the full proposal in Cycles of Time, released by Bodley Head in the UK and Knopf in the US in 2010. In 2018, he published with Krzysztof Meissner and Paweł Nurowski a paper titled Apparent Evidence for Hawking Points in the CMB Sky, identifying concentric ring anomalies in the CMB data that they interpreted as remnants of supermassive black hole evaporations from a previous cosmic cycle. The claimed Hawking points have not survived every reanalysis. Ingun Wehus, Hans Christian Eriksson, and collaborators at Oslo reproduced similar ring statistics using isotropic Gaussian simulations that had no cyclic history at all. Arguing the anomalies were consistent with cosmic variance, the model requires all particles to become effectively massless in the far future, a condition proton decay could satisfy, but which has never been observed. The mechanism by which information from one cycle transmits to the next has not been derived in detail. Critics have raised the objection that the conformal mapping loses too much information for a physically meaningful continuity. Penrose has responded to each objection. None of the responses has closed the case. Should Penrose's model hold up, the residual signal from a previous universe is already sitting in the CMB dataset your phone can download. The photons of a dead cosmos may be arriving now, encoding the last acts of black holes that existed before your Big Bang. If our universe is one of infinite cycles, is the memory of the previous one visible in the sky above you tonight? One universe may inherit another's last will. The next proposal denies before has a referent. Number 2. Hawking's no-boundary proposal. James Hartle at UC Santa Barbara and Stephen Hawking at Cambridge spent 1981 and 1982 working on the initial conditions problem in cosmology. The question of what boundary conditions general relativity's field equations need to make a specific prediction about the early universe. They wanted to apply the path integral formulation of quantum mechanics, developed by Richard Feynman, to the geometry of spacetime itself. In classical general relativity, the Big Bang is a singularity, a point where the equations produce infinities and stop being predictive. Standard cosmology forces you to specify initial conditions by hand at some early time and let the equations evolve forward. The theory does not tell you what the initial state should have been. Hartle and Hawking proposed something odd. If you rotate time into an imaginary axis, a technique called Euclidean quantum gravity, the singularity smooths out. Time near the Big Bang becomes a fourth spatial dimension. There is no first moment. There is only a smooth geometry with no boundary. Their paper, titled Wave Function of the Universe, appeared in Physical Review D, Volume 28, page 2960, in 1983. The proposal specifies a probability distribution over initial universes rather than a single initial condition. Hawking spent much of the following 3 decades refining and defending it, publishing extensively with Neil Turok, Thomas Hertog, and others through the mid-2010s. The proposal has not converged into a confirmed prediction. Alexander Vilenkin's Tunneling from Nothing proposal, published in Physics Letters B in 1982, gives the opposite sign for the wave function of the universe and predicts different observable consequences for the perturbation spectrum. In 2017, Jobfeld-Brugge, Jean-Luc Lenners, and Neil Turok published in Physical Review Letters a technical calculation arguing the no-boundary path integral does not actually converge and produces catastrophic amplification of perturbations rather than the smooth, uniform universe Hartle and Hawking described. Thomas Hertog and Hartle responded with a defense based on a modified integration contour. The dispute has not been resolved, and no proposal in this family produces a test we can currently run. On the no-boundary account, asking what came before the Big Bang is like asking what is south of the South Pole. The question uses grammar that maps onto no direction that exists. There was no before. The word does not refer to anything. If time itself has no beginning to point to, what does the word beginning refer to? One proposal empties before of meaning, this last one empties nothing of it. Number 1. The quantum vacuum that was never empty. Alan Guth's 1979 realization that a false vacuum could drive exponential expansion required an already existing thing to drive the expansion from. The inflaton field, the potential energy landscape it sat in, and the quantum vacuum that framed it all had to exist before inflation could begin. In the years that followed, a small circle of physicists, Andrei Linde, Alexander Vilenkin, Paul Steinhardt, and others, began asking the uncomfortable question of where that pre-inflationary structure came from. Classical physics treats empty space as empty. Remove everything, and what remains is zero. Quantum field theory tells a different story. Empty space in QF has zero-point fluctuations, virtual particle pairs appearing and vanishing on timescales set by the uncertainty principle. This vacuum energy is not a theoretical artifact. The Casimir effect, predicted by Hendrik Casimir in 1948 and measured to within a few percent by Stephen Lamoureux at the University of Washington in 1997, directly detects the pressure that vacuum fluctuations exert on parallel conducting plates. Inflationary cosmology requires that pre-existing vacuum to sit in a very specific state, a false vacuum with a particular potential energy and a particular curvature, for inflation to happen at all. The pre-existing vacuum had structure, it had geometry, it had specific values in specific fields at specific points. Guth's inflation paper, Inflationary Universe, A Possible Solution to the Horizon and Flatness Problems, appeared in Physical Review D, Volume 23, page 347 in 1981. Lamoureux's Casimir measurement was published in Physical Review Letters, Volume 78 in 1997. Alexander Vilenkin's 1982 Physics Letters B paper, Creation of Universes, from nothing attempted to derive the pre-inflationary state from a quantum tunneling event. But the nothing in his equations was not the ordinary word nothing. It was a specific mathematical object with definite properties. The derivations always import prior structure. Vilenkin's tunneling scenario requires the wave function itself, which is not nothing. Linde's chaotic inflation requires an already fluctuating field. Sean Carroll and Jennifer Chen argued in a 2004 paper on the arrow of time that the initial conditions for inflation must themselves be extraordinarily fine-tuned, transferring the mystery rather than resolving it. Carroll's later work on the Boltzmann brane paradox showed that many pre-inflationary proposals predict a universe dominated by random observer fluctuations rather than the structured cosmos we actually see. No mechanism has been produced that starts with genuine nothing and gets a false vacuum with the right properties. The nothing from which everything came had geometry. It had rules. It had a specific configuration that allowed inflation to proceed. Every atom in your body traces its lineage back to that configuration, and its properties were already fixed before your universe existed. What do we call the not quite nothing that came before nothing? Every discovery on this list sits at the working core of our best-tested theories: inflation, general relativity, quantum mechanics, quantum field theory, in the equations we teach graduate students, in the models that agree with data to 12 decimal places. When those theories are run backward far enough, they consistently return something that should have been there before there was a there for it to be in. The universe isn't confused about what came before it. We are. If you want to see more videos like this, click the video on screen now.